In this video, we'll talk about some alternative methods of counting. So first I'll say counting is an area of math that sometimes requires some out-of-the-box thinking. Sometimes the most straightforward, direct way is not the most efficient, and sometimes that direct method is even prohibitively long. In this video, I'll discuss a couple creative approaches that can simplify some counting problems. The first involves shifting the focus on what is asked. Suppose we have n total items. Of course, the total number of orders is n factorial. Suppose a restriction is given and we want the number of arrangements that meet that particular restriction. We have already talked about the way to count arrangements obeying many simple restrictions. Think of it this way. Every arrangement of the total n factorial must either obey the restriction or not. So let's say n factorial, that's the total number of arrangements. R is all the arrangements that obey the restriction that we want. Q is all the arrangements that do not obey the restriction. And obviously, all the arrangements have to fall into one group or the other group. So in other words, if we added up R and Q, it would have to add up to the total number of arrangements. Well, of course, that means that we could find R, the total number of arrangements that obey the restriction, by doing n factorial minus the number of arrangements that do not obey the restriction. So another way to find all the arrangements that do obey the restriction is to subtract the ones that don't from the total number of arrangements. And sometimes that's a much quicker, easier calculation to do. So think about this practice problem. 6 children will sit in a row of 6 chairs, but Jackie and Marilyn cannot be seated next to each other. How many arrangements are possible? Counting all the arrangements that meet this restriction would be hard. So the total number of arrangements without the restriction at all, that's obviously easy. That's 720, 6 factorial. Let's count the arrangements that don't meet this restriction. That is, all the arrangements with J and M right next to each other. Okay, they could be right next to each other on the left, or one seat over, or in the middle, or one seat over, or all the way on the right. And so what we have here are 10 possible arrangements that they can sit together. With any of these 10 arrangements, the 4 empty seats could be filled by an arrangement of the remaining 4 children in 4 factorial ways. So the total number of arrangements that do not meet the restriction, it would be 10 times 40. So 10 times 40, 240, these are all the arrangements that do not meet the restriction, the arrangements that have Marilyn and Jackie sitting next to each other. Well, the total is 720. And so the ones that have Marilyn and Jackie not sitting next to each other, we just have to subtract. 720 minus 240, and that equals 480. And that's the correct answer. That is the total number of arrangements that do meet the restriction that Marilyn and Jackie are not sitting next to each other. Notice that the prompt question contained a restriction involving the word not. These two could not sit together. That was the restriction. That can be a clue that thinking about the alternative way might be easier. The other strategy takes advantage of a kind of symmetry. We will begin with an example question. Pause the video for a minute. Just think about this question. Think about how you might go about solving this question. Okay. So 6 children will give presentations one after the other. Again, if there were no restrictions, the total number of orders would be 6 factorial, which is 720. Luke's presentation makes a reference to something mentioned in Ruth's. So Ruth's presentation must come sometime before Luke's, not necessarily immediately before. Could be immediately before, but it just has to be somewhere before. How many orders are possible? So Ruth's presentation must come sometime, anytime before Luke's. We could list all the ways that Ruth could occupy a slot before Luke, but that would take some time. Instead, think about it this way. For every order in which Ruth comes before Luke, so that's just a random order, C, R, B, D, A, L. A, B, C, D are just the other 4 students. So Ruth comes before Luke in that one. For every order like that, there's a corresponding order in which Luke comes first. Notice what we've done. We've just switched the place of Luke and Ruth and left everyone else the same. Those are two valid orders. They pair up with each other. One has Ruth first, one has Luke first. We can match these in a one-to-one pattern. And the point is, if we went through all the possible orders, we could match them all in this one-to-one pairing, one with Luke first, one with Ruth first. So think about this one-to-one pattern. This means that for every arrangement in which Ruth comes before Luke, there is exactly one arrangement in which Luke comes before Ruth. And again, it's just a matter of keeping everyone else the same, switching the place of those two, and then you get the matching order. Therefore, in exactly half, Luke comes first, and in exactly half, Ruth comes first. Because of pure symmetry, each one counts for half the arrangements. To count the number of arrangements in which Ruth comes first, we simply divide the total number by 2. So as we said, total number is 6 factorial, which is 720, divided by 2 is 360. That is the number in which Ruth comes first. Both of these approaches can profoundly reduce calculations if you notice that one is relevant to a problem. It's important to review these approaches enough and practice them when they are relevant so that they are on your radar when you analyze a new problem. In summary, if you are asked to count how many arrangements obey a restriction, it may be easier to count the ones that do not and subtract them from the total. And in any question that's asking about two terms to be in a particular order, one order and not another order, think about whether the two groups are related by symmetry.